This is our first podcast for SpaceRouter Onion. Yeah, let's get started with introductions. So we have three members today, myself, Maxime, and Caue. A bit about myself. I manage the engineering here at SpaceRouter Onion. And my experience is a little bit on the transactional side. I started with like point of sale systems that were restaurants. Eventually, they wanted to get those sales into reporting. So brought them up, did a bit of business intelligence around it, introduced me to anything restaurants and software. Eventually got into credit card as we moved from cash to credit card and banking. And eventually when I got introduced to crypto, which is also transactional, so that's how I got into crypto. I'm gonna let Maxime introduce himself next.
So hi, I'm Maxime. I'm a Rust engineer with a focus more on the low-level networking. Before I joined SpaceRouter, I actually spent a few years at Threefold, where I was building an IPv6 overlay network, which we call Maxime. So yeah, that's mainly my part of.
Caue?
Yeah, my name is Caue. I mainly work with banking solutions and payments. My last experience with payments was like supporting millions of users and high volume, high load. Also, I'm a software architect and helping David and Maxime here with solutions for this project.
Very nice. And can you talk a bit about what is SpaceRouter Onion, Caue?
Yeah, sure. So SpaceRouter Onion is our decentralized proxy network that allows users to have privacy when navigating through the internet, doing usual stuff, and don't want to be like identified or have the tracks while it's navigating. Yeah, that's the main thing. And you have like also a next slide to show how it works for the user itself as a user experience. Everything starts with the app. So you install an app in your local computer. It supports you Windows, Mac OS, and Linux. And with that, we have like a wizard, a simple setup wizard that will install the selected proxy. We have two versions that we are going to talk this in the future conversation, in the future. When you install the proxy, we also have instructions to install the browser extension. The browser extension is responsible to enable the proxy browser to connect to our SOCKS5 proxy that is already installed by the app. And that's pretty much it. You have two things installed, and all your navigation then will go to the SpaceRouter Onion network. And how does that work? It works like the proxy that is running locally is connected to the guard node. So the guard node receives this request and then sends to the mid node. The mid node only knows about the guard node that sends this to him. It doesn't know about the proxy. So you are already forgotten by the network at this point. The mid node will send that to the exit node. The exit node is the last hop before the internet. So the exit node only knows about the mid node. The guard node is already forgotten on this step. And then the internet receives your request, prepare your response, send back to the exit node and everything back to you. And this is how the privacy works. So each step only knows about this surroundings, not about the whole circuit. And yeah, that's pretty much it.
Maxime, can you elaborate a little bit, like how does this is different from a traditional VPN?
Yeah, so the SpaceRouter Onion is a VPN. With a VPN, you're basically asking you to trust the company. They see everything, so every site you visit, every server you connect to, and you rely actually on their promise of the privacy. The thing that we do is that privacy is actually a property of how the network is built. So if a VPN provider, for example, he gets subpoenaed or hacked, or he just decided one day to start logging, there's nothing technically stopping them. With us, we don't have a single operator in the chain that has both the ends of the conversation, as Caue just explained. So even if one node is compromised, it learns nothing useful. So that's like the main difference between us and a traditional VPN. We have built the architecture around privacy and not based on just a promise.
Awesome. And maybe you can elaborate, like, because obviously we're part of Tor, do similar things.
So yeah,
a little bit different.
indeed, there's a lot of same things with Tor. So Tor is, of course, a beautiful piece of technology. We owe a lot to it. But the thing is that Tor actually relies on volunteers, and the discovery of who's a relay goes through small sets of what they call a central directory authorities. So that's a centralization point. And that's also the reason why Tor isn't that big, despite it being like a few decades old. We actually took a different bet. We want to make it economically incentivize people to run a node, because if you contribute to bandwidth, you get rewarded on chain automatically via smart contracts. So that gives us a much bigger pool of potential operators, because you're not asking people to donate their CPU for free forever. And then the other piece that's of course related to that, but Caue will talk more about that, is the discovery, how we deal with that. That's also different in our network than it is with Tor.
Okay, so let's talk a bit about what's coming later. So the first thing we've released today, at least, is a functioning network, and we don't yet allow people to join the network, even though it's the mission, right? It'll come, because we need to find a way to define what is a functioning node and how well does it function before we influence the selection. So the next things that are coming is the ability to have some off-chain oracles that would vote on the performance of the nodes and how well they're doing. Once we have this, we can allow decentralized participation, and we can influence the node selection. So when your client is selecting which hops it wants to use, then it's not just saying, oh, I'm using random nodes. It's going to say, oh, let me use a guard node that has been online for a long time. This way, I'm not changing guard nodes often, and my privacy is kept. So this is the big milestone is this. Now, on the long-term vision, we haven't done it yet, but the long-term vision after reputation is how do we authenticate the client, and we need to authenticate the client to the nodes without revealing who it is, and that's a very difficult mission, but we have some good progress on the research on that. But that's one of them, and the second one is permissionless settlement. So where the nodes are going to be paid, where the clients are paying without leaking their privacy. So the next part of this call is a discussion about how we built this protocol and different things. And I'll go first. And so when I start a project, the first thing I always kind of try to figure out is like the vision, but also how it's going to work. And we didn't know yet, is it going to be a software? Is it going to be the whole computer traffic? Is it going to be, I think there's some feedback. You can your microphones. Maxime and Caue, I think you mute your microphones, if you don't mind. So yeah, when we build the software, at first we need to make sure that like you understand like how the user is going to use it, and then you start building. At least that's my mental model when I build software. So we couldn't build the whole software in an extension because extensions are kind of like JavaScript only, and even if you go into like service workers, you end up in not in the most favorable languages for performance, but also like essentially it's very hard to build an extension that can do this kind of protocol. So we were trying to figure out like how can we do it, and this is where we came up with the conclusion that you can have a binary living side to side with any browser. And we obviously did not want to build a whole browser, so we didn't want to go the route where we have to start maintaining this Chrome Onion browser. So we just built an extension that can switch on and off the proxy setting. And this is where we start thinking like, okay, what kind of proxy? There's two kinds of proxy, HTTP and SOCKS5 proxy. And the SOCKS5 proxy is more interesting because it could keep a connection open. It actually focuses on TCP and not HTTP compared to an HTTP proxy. So it'll give you support for WebSocket, Socket.io, and a lot of things that websites use. And so we just built this small prototype, and this small prototype was just calling this random small node living on a cloud. And oh, great, your extension is switching off the setting and you have the IP that's on the cloud. Great. So we know that this would work. And this is how we build the foundational of like what Caue was explaining. We have this proxy on the machine and we have this extension. This extension turns on the proxy settings, which uses this SOCKS5 proxy. And from there, we can translate into our protocol. And then I think I'll let Maxime start the conversation about how we started the protocol and how it came to be.
Yeah, so we started off by actually, just like David said, in the beginning we had nothing, and then we did a few little tests, and eventually we came to like our first single hub circuit where we added some security inside. So we came to single hub circuit, one client, one node, end-to-end encrypted, and then we started evolving quite quickly towards realizing that we could actually use a different transport because we were only using TCP in the beginning. But we eventually discovered that QUIC would be a better option here. So now we use QUIC between the different nodes, which QUIC is a new transport. It's built on top of UDP, and it allows us to multiplex many independent streams over a single connection without the head of line blocking that TCP has.
Can you explain a little bit what head of line blocking is?
Yeah, sure. And so in TCP, you have a guarantee that every data that you send comes back in the exact order as it was sent. So if there's one package that got lost in transit, the TCP halts the delivery of all the other packages that are behind it. So that's actually the head of line blocking. We don't have that problem in QUIC because we use independent streams. So unlike TCP, QUIC provides multiple independent concurrent streams within a single connection. So that means that the multiple pieces of data that you wanted to transmit are placed into separate streams. So one slow piece of data that you want to fetch doesn't block all the other pieces.
Awesome. And I guess, Caue, you could talk a little bit about how the network. We have this like function onion protocol, but like how do the clients pick which hops to use and what comes into play?
Yeah, sure. So I joined the team like a bit late than you guys. Initially to help with this satellite services, to not the core of the Onion, but lately I work with that. And one of the first services that I helped you guys develop was the Network Discovery API. The main idea of the Network Discovery API was have a way to provide to the proxies a list of what are the available nodes that you have for that network that you can connect as guard, middle, exit nodes. That was the first goal. So to achieve that, we need two things mainly: how the nodes are searchable, right? And how we are going to select them in the proxy. So the first thing was for the nodes to register itself somewhere to be found, and the smart choice that we have here for them to be registered in the blockchain. So we work together with the smart contract team to provide smart contracts for the nodes to register itself in that chain, and then the Discovery API will go there and fetch those nodes, cache them, and provide to the proxy. That way, we avoid adding pressure for every proxy to connect to the nodes, to the chain, to get a list of nodes and solve the path. The
And
second,
how do we like essentially how do we know which nodes is, I don't know, like let's say there's different node selection on our proxy, right? Like there's the speed, there's the maximum privacy, and there's random. So random is obvious, it's just randomized.
yeah, that's random. Yeah.
How do we know, how do we decide what is for speed? And
Exactly. So this is how one of the second things that the Discovery API does. With the list of nodes that we have already registered in the chain, so we get them and we resolve the geolocation for each one of them. With that, so we decide, okay, this fast, we have 3 modes for the proxy selection, for the chain circuit selection. One is the fast, like we said, the privacy and random. So for the fast, initially we decide, okay, let's get the closest nodes from the proxies and build the circuit around that. That worked, but it's not completely cool because each one of them can be, it can be also always the same because it's always the same closest one. So we decided to move that to, okay, let's get the first for the guard node, we get the closest from the proxy. For the middle node, we get the closest from the guard, and the exit node, the closest from the middle node. And then we have like a path from that to the internet. And to avoid like the deterministic selection, okay, always the closest to each one, we added some weight to them, so it's kind of add some randomness in this selection. It's close, it's too close, but can be this close or that close. So we have this definition of close. What's close, right? The definition of close can be a little farther or closer.
yeah,
For the private mode, we did the opposite. So we get the farthest, and then from that, the farthest from that, and so we like around the globe to reach the internet. Of course, we compromise the speed, but we increase the privacy. And the random is just random nodes we get them and provide them. So that's more my first contribution to the project.
And can you talk a bit about like, okay, great, like because we say, hey, we don't have a central authority, but now we're saying, hey, use this API, and this API is like one API that everybody is using. So how can the proxies, or let's call it the SpaceRouter Onion client, reduce its trust into this central API?
Yeah. So that's a good question. For that, we are not trusting the Discovery API for the nodes. The proxy itself, it also validates the list of nodes that we provide, or not the list of nodes, but when the proxy receives the list of nodes, it provides, okay, let me select these 3 nodes here. And for each one of them, it will validate if the node is valid, it's still active, or anything else in the chain again. So, but not all, but for the selection that we have. If that's not valid anymore, so that node will be like in a cooldown list. It will not be selected for some specific amount of time, and then we will reconstruct the circuit with another node provided by the discoverer and validated against the chain. So we have this layer.
So the node can always decide to just not enable the Discovery API. They can decide to
introduction.
Use the RPC and it like maybe configure it, not yet, but eventually we could add that they can configure their own IP, because the biggest problem essentially is like the node needs to know the location and the nodes to choose what is faster, and the way to do that is it needs to resolve the location of those IPs, and that is not free. So this API provides this accommodating free but still verified on chain. But if someone wouldn't want to trust it, they could technically configure it with his own API key, his own, resolve the location of all the nodes and not depend at all on this Discovery API. Let's go back to the protocol a little bit. So Maxime, can you talk a bit about like what was the most surprising to you about implementing this kind of protocol?
In the beginning, it was of course a bit of a shot in the dark. So we started off without a protocol, but we quickly realized we needed like to spec out a decent protocol. And some other things that was really nice to have was actually we have a Go implementation and we have a Rust implementation. And actually by having 2 different implementations, that showed us that everything that I thought was right in the Rust implementation turned out to be against. So building 2 implementations with the same spec was actually the fastest way to finding out where the things that were wrong in the spec were. So eventually we ended up with like two code bases. We had the Rust code base and the Go code base. They were all dependent on one spec. And then we did a massive cross-checking. We found dozens of places where the spec was too ambiguous or just not enough. Where Rust did the thing one way and then Go did the thing another way. But then eventually, after a lot of fixing and a lot of rewriting the spec and making sure that both implementations are perfectly aligned with the final version of the spec, we got it working. But then, of course, then we hit the next big milestone, which was like opening it up to users. So the first big part was actually building it. The second big part was actually making sure it doesn't break once people started using it. And of course that also was an iterative process. We sometimes had to make little changes to the spec again because it was a very iterative process. But eventually we got there. We have a working Rust node, a good spec, and a working Go node as well. So that was something that really stuck to me. Like making two different implementations for one spec was really insightful to actually see if the spec was written well enough. So that was something that really stuck to me.
Awesome. And Caue, can you talk about what was the most challenging to you?
Yeah, sure. One thing that I can mention that was a big challenge was the testing, how to test everything, because we have all this complexity. Sorry. All this complexity about install the nodes across the globe. We have proxies, we have traffic key. We need to add some real traffic to this network to make sure nothing's broken, everything's working, the circuits are active and everything. And there's also a funny story that I have an old laptop here that I was testing the network, and for some reason the old network board of my laptop was disconnecting from my Wi-Fi, and we found a bug in the circuit that was not keeping the circuit, and we discovered because of this old laptop. So that was a good test, but we got by luck. But yeah, the testing was a challenge, but we achieved that. And also the volume of traffic that a single call to a page generates in the sessions, the circuits, and all the network. That is a interesting fact. Yeah.
I'll talk a bit about what surprised me the most. I mean, many things, obviously, but like Caue said, the first pages that we test with are like the ones I never visit, because like if you visit msn.com or yahoo.com, I mean, sorry for hitting the old giants, but like they're just like news pages with thousands of images and videos being loaded at the same time. And it was just surprising that one website can open almost 2,000 connections, which like the early limits of admissions we put were too low on bursts. Like we would say, oh, 2,000 TCP stream should be a good limit or 500 could be a good limit per circuit. And just opening one page, you bust that limit and nothing works. So that was very eye-opening. Other than that, like we kind of decided naively, but for the right reasons, to use QUIC right away. But like we didn't know the implications right away, and I think this is a cool conversation because like if you understand Tor, you understand that like there's a counter for the forward messages and there's a counter for the backward messages. But because TCP doesn't allow messages to come out of order, which is a huge benefit of QUIC itself, to reduce the yellow light blocking like we talked before, it's very easy to count those counters because they're always in order. But now that you can send messages out of order, you end up where you have to deal with that. And maybe Maxime can talk a little bit about that, which is an interesting point.
Yeah, so I can remember that bug. It still haunts me a bit. So what we had is actually the counters were going out of order. So as David explained, every message has a counter, and that's actually used as a replay protection, so that the receiver can check, have I seen this number recently or not? Because if it has seen that message already, it can assume that maybe someone is trying to replace the message. And in the bug, we actually had two tasks that were both pulling characters from a shared pool. And they sent them on different channels. So what would occasionally happen is that a higher number counter would arise before lower number one. The receiver would think it was a replay attack and it turned down the circuit. And then eventually we managed to fix it by introducing an ordered sender, which is like this single component that owns the counter allocation and the write out of it, so that the order on the wire matches the order that the message get allocated with.
Yeah, and for me, like, you talk a bit of, like, we'll talk a bit about the challenges. I think one of my challenges was like QoS, like how do we provide, because like you have a bunch of connections going through those relay nodes, and how do you make sure that one doesn't like overtake the whole bandwidth? And I think this is like props to the people at Tor, which we are inspired of. They put a lot of effort in that. So, and the amount of research and maths that went into it is like mind blowing. But there's like almost three systems that are all happening at once that don't need to know about each other. There's the obvious, like, oh, as a node, I don't want to offer more than this amount of megabytes per second, and we can call this like the bucket rate limiting. And then at the same time, there's also like this UMA protocol, which is making sure that like when nodes are sending information or through those relays, they kind of get a turn at sending messages. and what's very interesting is like the way they were designed is that they are not based on time; they're based on like sequence of operations, which is very, very, to me, a challenge to implement, but very, 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 very like genius engineering. There's another one which we don't have yet, but we plan on adding it, which is how to deal with back pressure, like where a node knows it can send about 1,000 messages, let's say, and when it sends a message to another relay node, it assumes that its counter of 1,000 is now at 900, 800, and it will never send more than 1,000. And when the other node has acknowledged those messages, again, not time-based, which is very interesting, it'll just send a message back to say, hey, you can reclaim those 300 messages you send me, and your counter goes back to. So the interesting thing that it does is it reduces back pressure between the relay nodes. So the proxy on the other side doesn't need to respect it, but all the nodes prevent back pressure for a given circuit while they share connections. And without this, you would have a lot of overstepping. And what's very interesting is that those three protocols do not step on each other. They don't need to rely on each other. The global rate limiting is just a global rate limiting. The UMA is an ordering of which cells can go first and second. And the send window is, again, not related at all. It's just between relays, they kind of like back pressure each other. And together they work as a very good quality of service to make sure that nobody's overtaking this. And I want to ask, like, again, Caue, tell me what you felt was a big challenge, whether if it's running a node or testing or anything, whatever you can come.
Yeah, we already give a good example about the core of the node, but probably I can give one more about how the project runs itself. So I already mentioned the testing, how to test is spin up nodes, like we have the blockchain registration, so that was already mentioned. I think another one was like having two implementations for pretty much everything, like Go and Rust for the nodes, for the proxy, and that made us have like a good specification, a good documentation, avoid ambiguities, because we got tricked by the ambiguity sometimes that one thing was implemented in one way in Rust and another way in Go, kind of having the same result in the end, but mixing in the middle. Also, the entry points or the arguments of both was kind of mixed. So that was a great challenge, because It's not only, okay, let's have documentation, but we need to avoid ambiguities and be clear and that's it. It was not a challenge, but was a good thing. Well, if you're going to talk about high points in the development process, but the team integration, I think, was something that we need to manage. Like we have some smart contract teams, we have design teams, we have QA teams, and we have the development teams all working together with different priorities. So that was a good one also to work and help in the process.
Maxime, maybe you can elaborate a bit again, like on some difficulty. What do you think was the most difficult thing that you had to that you had to work on this project?
Well, actually, the most difficult thing I think was actually getting to nail down the spec and dealing with the counter issues and the nonce issues. But then another thing that only like was done more recently was when we started opening up the network towards real users, or at least in a closed open testing. We saw that some things were going wrong. We didn't know what exactly, because of course sometimes you can have flaky nodes or connection just randomly interrupts. So then we built this testing harness around it, which was also like quite fun to do. We call it the sanity bot. It does a few things, like it makes a matrix of all the possible circuits that you have in your network, and then it walks through them. So every guard, every middle, every exit, and that increases exponentially. So you have like thousands of combinations. And then for each one of these circuits that it can create, it's going to spin up a proxy. It's going to build a circuit, and then it's going to make a real HTTP request to it and verify if everything works. And then some fun things that were also like quite challenging, because sometimes things misbehave. So we also included that in our testing harness. We have the Chaos module, which deliberately misbehaves on the network layer. So for example, it stops, it drops a handshake midway, or it holds a TCP connection idle, etc., or it aborts the quick handshake. And by doing this, we actually managed to find a lot of bugs that were not immediately noticeable at first when we were just locally testing it. So that was quite challenging as well, like actually dealing with the bugs once once real traffic started flowing through it. Yeah.
So the next thing I want to talk a bit about is like AI. And I mean, like it's obvious everybody uses AI, and I didn't want to start with that because like I find that all the technical videos is AI everywhere. Like we can see a bunch of memes online, the video about Google presentation, and they've said like AI maybe 5,000 times in 5 minutes, but I'm exaggerating. So, but it is a topic. So, and actually, I find it like it was an accelerator in this project, but it has to be done in a certain way. And I think one of the interesting things that we had to build as a team was like some logging that is not always enabled, that would allow the AI agent to detect anomaly. And obviously it consumes a lot of tokens because it reads like thousands and thousands of events and says, well, this event should have happened before this, and I think this is because this line of code did this. And so, but on its own, the logging locally can only work to some extent. So we had to build like this simulation, which we internally called the zombie network. It's a little bit inspired of like the Polkadot blockchain zombie network, where it will spawn a bunch of nodes, it'll spawn a bunch of proxy, it'll run a lot of curls and speed tests through it. And at the end, we can collect this data and then we can analyze it. And we enable obviously all the kinds of sensitive log. And I think this is interesting. Like AI needs a lot of data, but it also creates, sometimes it hallucinates a bit of a problem. And it almost tries to create too many guardrails. So Maxime recently had to like find a problem that's in the open testing. And we kind of like matured to understand that, okay, AI can tell us potentially what is the problem, but how do we know it's the real problem? And forcing it to create reproducible steps and confirming it and making sure we don't create too many changes that will actually break more stuff. How did that go? Can you talk a bit about it?
Yeah, well, I agree with you. Everybody is using AI, so we are also doing it. But The thing I've noticed exactly when because I encountered these bugs is that we actually, at a certain point, all the three of us, we took a step back and we were thinking about how can we actually solve this and still make advantage or use AI in our advantage. So I think now it boils down to that we have a very doc first, so documentation first, specification first approach, and then also, of course, what's really important is in testing. And I think that by combining good documentation and good specification, and actually carefully watching what the output of the code is that AI is generating, if you have a good, well-developed testing harness, and as David said, the sensitive logging and all the other tooling around it, that you can really be sure that it's actually behaving the way you want. It actually accelerates the process a lot. But I think a prerequisite for that is actually having the tooling around it, having documentation, because if you just let it loose, it hallucinates, it does its own thing. And that turned out to sometimes come back to us to bite us in the ass, but eventually we got it through. But I think, we evolved towards using AI in a very documentation, specification first approach, and then a lot of testing and a lot of insights into what is actually going on behind the code. And I think once you get that stack, AI is actually very helpful, and it can guide you towards the correct destination much faster than it would if you would manually develop everything.
Maybe Caue, you could talk a bit about your experience. I know we added a lot of it used to be very hard to maintain like UX integration testing and things like this for the apps, but you also played with the zombie network a lot. So talk a bit about the zombie networks and like how we automate testing a little bit with AI.
Yeah, sure. Yeah, like I mentioned before, and also Maxime mentioned now, I think the biggest challenge to work with AI have like this good documentation to avoid ambiguities, or like not provide the 100%, it's very difficult, but a high percentage of clarity to the AI. So that was one of the challenges that we have and one of the difficulties with AI, but it accelerated a lot. And with the zombie network, the zombie test that you just discussed, I think the importance of AI there was to like verify the results. That was where we use it most, because running that is just okay, like a CI/CD pipeline. They create machines here, servers there, run things, run this script, and that's it. But after that, we have, I don't know, the amount of data of logs that would be like human impossible to read and correlate things. So that was like big acceleration by the AI, because it could track everything. The AI has already the context of the code, knows how the code works, where the log should be placed, and checking different connections and the nodes and everything. That provide a lot good reports to us to check if that result was good or not, because in the end, what we'll see, okay, we'll see it works or not, and that's it. But with AI, we could go in the details and say, oh, it works, but now it's slower, now it's faster, now we have some dropped connections here, and so on. So we have more data.
That, like the zombie network was designed to be analyzed by AI, because like you said, a zombie network is finished. The only thing it gives you information, but it doesn't tell you if everything went well. It gives you the logs. It gives you what the circuits were for each proxy at what time. It gives you the result of the speed test. It gives you the results of the curl test. But it doesn't tell you if things went wrong. It doesn't tell you if circuits were destroyed and recreated in the middle. It doesn't tell you anything. So AI, like you said, in an unhuman able speed, will just read 40 megabytes per node of sensitive log. And I don't know how. I don't know if there's optimization in inference or anything, but it kind of knows where those logs come from. And with enough context, like it found problems that we didn't even know about. It just found random anomalies. But it also does, like, it creates this reassurance that every PR, even if it's small, we run the zombie network sometimes multiple times if we're worried about that change. It creates this reassurance, like similar to how integration tests used to do it, but in a less deterministic way, maybe. So that's quite interesting. So I'll let Maxime and Caue, Maxime first, maybe do an exit statement about before we stop. So go ahead.
So yeah, for me, this was quite. This was an amazing learning experience thus far, and there are many more things to come. But for me, just the most satisfying part was actually like watching this now formal code base become something where people can actually depend on. And the credit for that is shipping on tight loops, having the two implementations to keep each other honest, and writing, of course, the test harnesses before you need it, rather than after the outage. So yeah, that concludes it a bit for me. It's honestly an amazing project to work on, and I look forward to what we will be able to achieve in the future.
Caue.
Nice. Yeah. So yeah, I think the most thing that I'm getting so far is the learning, all these concepts about networks and all these details that it was kind of new for me to go so deep in those implementations and details. And also, I think it's like the satisfaction of see how this could impact the people's lives, right? They are using and running, and you see, okay, yeah, this is happening. Your privacy is kept, so don't worry, it's just working. Yeah, this is good.
I'm on my side. I think I learned a lot about networking. That's for sure. I learned a lot about QUIC, even the concept of headerline blocking, UMA, bucket rate limiting. Everything is actually quite new, but the most exciting will be the next steps for me. Like, I'm a blockchain guy, so how do I get this on chain more? How do I allow outside participation? How do we rate if a node is behaving properly? And even more on the next steps, like, this is always like, I'm very hungry to knowledge, but how to figure out how do we auto settle this in contracts without breaking privacy? We have some research. We think it's going to work. If not, we'll find another way. But a lot of zero knowledge, Grad 16, a lot of smart contract optimization about storage. There are some very interesting things coming to EVM later that could even save a lot of gas, but cost on chain. Yeah, I mean, just exciting stuff. I guess the closing statement would be, outside of that, is like, I think everybody here agrees, is like, we want you guys to use it. We want more users. We want people to use it. We want feedback. So follow us, use it, tell us what you think, and we'll just keep on making it more private and more solid, and hope and increase the network's usage is what we want. So thank you, Caue. Thank you, Maxime. This was awesome. Hopefully we can do more of those. I really liked it.
Yeah, thank you, Dave. Thank you, Maxime.
Thank you, everyone.